All right, welcome everyone to So You Want to Make a Multiplayer Game. I'm going to get started straight away because this is a long talk and I've got a lot to get through. So first up, get the presentation working. Technical difficulties. Hi, my name's June. So, why are you listening to me stand up here talk about multiplayer? Over the last 6 years, I worked on a couple of multiplayer titles. Unfortunately, neither released. I've done a bunch of open source networking protocol work and like implementing replication and input prediction for an open source game engine. And I'm now at Network Next, where we're working on reducing latency for online multiplayer games. And I'm here to teach you today how to do things like write the network protocol, implement input prediction, and that sort of thing. First up, why do we even want to make multiplayer games? They're quite difficult. But if we look at the market, online multiplayer is a huge market. It has 30 times more annual revenue than offline PC games. So if you want to, be in a business of making money, multiplayer is a pretty good way to go. So an overview of what I'm going to be talking about today. I'm going to be talking about protocol design. How does the game client and the game server even talk to each other? I'm going to be talking about multiplayer architecture. So how do we synchronize the game state over that connection? And the design impacts of that, like how does that impact your game design? And there's a few other bits and pieces, and then we'll hopefully have time for Q&A at the end. So straight up, let's get into protocol design. What do we need for real-time multiplayer? So to be clear, I'm not talking about turn-based or asynchronous games over REST or anything like that. We're interested in fast-paced, real-time, where we can get information from the server to the client as fast as possible and have the most up-to-date information. So importantly, we want to know when a client is connected. We want to be able to control reliability. So for example, if I'm sending the player position over and over and over again, I don't really care about old information. All I want is the latest information. And depending on the type of game you're making, you might want to be able to send large messages. So that is messages that don't fit inside a single packet. And then there's a few network-related things we need to deal with, like congestion and flow control and sort of stuff. First up, don't use TCP. TCP is a reliable ordered stream, and what this means is you can't control reliability. So just as I was saying, we only care about the latest information. TCP has head-of-line blocking, and it doesn't let you turn that off. So your game will stall if you have packet loss, and it will sit there waiting for old information that is no longer relevant. So it's not suitable for real-time protocols, and we need to use UDP. But UDP on its own is connectionless, so it doesn't actually give us a concept of a connection. All it is just fire off a packet. The receiver will hopefully get it, maybe, and then that's it. And there's no idea of a connection or anything like that. But as I mentioned before, we need connections. We need to know when players are connected. We need to know when they're going to disconnect. So we need to kind of design like a connection protocol on top of UDP, right? And we can actually take advantage of our particular requirements for this protocol, right? We don't necessarily need to have the connection negotiation you might see in like TCP, because for real-time multiplayer, we're constantly sending updates to the server and client. They're both talking to each other very frequently, in fact, on a regular tick rate. So we can actually cheat and say that the continued presence of packets is what indicates a connection. We don't need to explicitly go and set one up. We can be like, oh, hey, I got a connection from this IP, therefore, I've got a connection from that IP. And then if we don't see packets for a certain period of time, then the connection times out. So on your server, you can just map, you can just have a hash map of like IP endpoints to the game clients. And yeah, when it gets a new packet, it just implicitly creates the client if it doesn't already exist. Let's do a bit of a live demo. Fingers crossed this works. So for all the network connection stuff, I've got some. Oh, you can't see that. Some nice demos open here in Visual Studio, and I'm just going to run through these real quickly. All the source code is up on GitHub afterwards, so if you want to check it out and have a look at how it's all implemented, feel free to do so. So let's just go over here, and we're going to run a server. Oh, it's launching on the wrong screen, so this is going to be great. And a client. I apologize, I can't quite see. There we go. So here we go. We've got a client, we've got a server, and it's talking to one another. But let's try and simulate like a real world network, right? Let's introduce some packet loss, right? Because that's always fun. So let's start dropping some packets, and just to make it really obvious what's happening, let's just drop like 90% of all packets. This is a horrible connection. But what you can see here is that the client keeps on sending packets. Like, sure, well, okay, I guess it disconnected. That was too much packet loss. There we go. Let's reduce that a little bit. But you can see that the server is not receiving packets from the client, and the client doesn't know anything about it. So you can imagine that if I'm the client and I'm, sending an action like I want to use an object or open a door, for example, and nothing happens because the packet gets lost, that kind of sucks as a game experience. So we really need a way for both the server and the client to know if what they send actually gets there. We still want the ability to tell tell if things get there, even if we don't always want reliability. Just move that back over there and move the Visual Studio out the way. All right. How are we doing on time? Okay, cool. So, I just kind of went through all of that. So reminder, in our protocol, we're constantly sending packets, right? So what we can do is we don't actually need to explicitly acknowledge packets that we've sent, because we're already sending packets anyway. What if we just put the acknowledgement in the packets we're about to send? And so if you imagine, here's a server and a client. I hope these diagrams make sense. So we've got a server and a client. They're sending packets to one another. And then let's think about this packet right here. So the server sent a packet to the client, and the client is now sending a packet back to the server. We want the server to know if that first packet it sent out was received by the client, right? Because maybe it's really important. Maybe it's like a login message or what have you, and the server might need to resend it if needed. So to make things clearer, in order to do acknowledgement at all, we need to give our packets IDs. And these are called sequence numbers. In our protocol, we're just going to use 16-bit integers. And I've just prefixed them here just so we can see in the diagram. Hopefully it's clearer as to what packets are going where. So what we can do is we can take, when the client is sending packets out, it can track what packets it's received. And then it can embed information about, oh, well, I got sequence number 1 from the server. And it can embed that information in the packet it sends back to the server. And then the server can be like, well, the client got sequence number 1. Great, I don't need to resend it if it was important. So this kind of works great. But what happens if the packet going from the client back to the server gets lost, as in this example here, right? So the server knows the client got a packet with sequence number 2, but how does it know that it got a packet with sequence number 1, right? If it never got the packet from the client, that doesn't necessarily mean that the client never got its message in the first place. So if we look at our packet structure so far, it's very basic. We're just going to be including a sequence ID for the packets that are going out. So these are just incrementally increasing a sequence number going from, for example, the server to the client. And then it's also including an ID, which is the acknowledgement number. That's the most recent message that you received from the remote computer. And so you're saying, well, the last message I got, say I'm the server, you're saying the last message you got from the client had a sequence ID of 45. So what we can do is we can add a bit field. And a bit field is basically you just take 32-bit integer, which has, surprisingly, 32 bits. And you can use each one of those bits as a Boolean value. And you can think of this as sort of like, kind of like a history of what you are also acknowledging. So for example, if I'm acknowledging packet 45, I can then use the 32 bits that I have to acknowledge up to 32 packets in the past, 44, 43, 42, 41. And of course, I can always also explicitly tell you when I've lost a packet, when I didn't receive a packet with a certain sequence number. So now, when the packet is lost, we can say, oh hey, in this packet that we're sending back to the server, I actually did get the server's sequence 1 packet, because I can say I'm acknowledging server sequence number 2, and the bit field specifies that the previous packet, since we don't have a long history here yet, the the previous packet is also acknowledged. So the server knows I don't need to resend that. The client has got it. All right, and this basically continues throughout the protocol. And so, for example, in this case, you can see that the client is acknowledging that it's got server packets 2, 3, and then it misses 4, and then it sends 5, and I've got 5, but hey, I missed 4. And then what you can do is you can say, well, demo a bit early, and then you can detect whether or not you need to resend packets and then correct for that. So, demo time. Let's jump over here. All right, let's do server and a client. Oh, that's right, other screen. So, I've still got the packet loss on, but you can actually see here. Hopefully, it's not too fast. But you can see that the client is able to detect when the server is not receiving the packets that it's sending, and then at the application level, you can do whatever is important or whatever is appropriate. If you're just sending like player position data from the server, it doesn't matter. You're going to send more player position data pretty soon anyway. If it's really important, you can resend it again, and it lets the application or your game decide what it needs to resend. All right, back to here. So we've got connections, we've got acknowledgement. Let's think about large messages. So because UDP is not on its own, it doesn't provide connections. The largest amount of data you can really fit in a packet is about 1,500 bytes. So if you want to send something really big, say you want to send like a map, for example, down to all the clients, well, you need a more reliable way of sending that. You need a way of splitting that information out across multiple packets, and then also making sure that all of those parts or fragments of that message get down to the client, because obviously if you get 99% of those messages, it's not really useful. You can't do anything with only 99%. So don't try and use TCP for this. It can be tempting to be like, oh, well, you know, in this case I do need to send like big reliable messages. Can I use TCP? Well, there's research that shows that using TCP actually induces packet loss in UDP protocols. So you'll start sending stuff with TCP and suddenly your UDP connection that's sending your player data or what have you starts getting even more lossy, and that just creates a poor game experience. But we actually have everything we need to implement this on top of the protocol we've already written. And we can actually be a little bit smarter than TCP, because unlike TCP, which will basically block if it detects that it's lost a packet and then resend everything, we can actually just resend the bits that we've lost, right? We already know on a per packet basis whether or not a particular component is lost. So what you do is when you want to send a large packet that spans multiple things, you basically determine the maximum size of the data you can fit in a single packet, which is MTU is a maximum transmission unit. Again, it's about 1,500. You need to take off space for like the headers, and then you split that message up into those kind of components. You give each message an ID. This is separate to a sequence number. You want to have an ID that is consistent for all the fragments, so that if you're sending multiple large messages at the same time, the server doesn't get confused and reconstruct them incorrectly. It can track each message independently. And then basically you include some information about, you know, what index fragment is this in the list of total fragments, and how many total fragments are there to reconstruct. And then you send each fragment out as its own UDP packet. When you receive a fragment, you basically look up the reconstruction state for that message, and if you don't have it, then that's probably the first fragment you're receiving of a reliable message. And then you can look at the fragment index and the total number of fragments and the IP address you're receiving the message from, and get all the information you need to start reconstructing the total message. And then as you just receive fragments, you just copy their data into the buffer in the right offset based on that fragment index. Once you've got all the fragments, you can pass the message back up to the application or game, and there you go, large messages. There's a few extra bits. Again, you need to listen for the packet lost event on the sender, so we already have that because we have acknowledgement. And then you just resend the packet if it got lost. Live demo again. So let's have a little bit of a look. Again, let's rise. We can. Oh, I've still got packet loss on. I'm going to turn packet loss off just for this. I think it does work if we just kind of do like 10% packet loss, but as you can imagine, if you're splitting out, if you're splitting up lots and lots of packets, if you have like 90% packet loss, it starts to get very hard to like reconstruct a message when you've got like 90% of packets aren't getting through. So as you can see, we can send about 29 kilobytes over this protocol, and this can you can just expand on this to send messages of whatever size you need. Cool. A few more things that you'll probably need to deal with. So flow control. If a player has like high latency or high packet loss, what you can try and do is reduce the send rate of packets. And so basically this is a scenario where either the player's bandwidth or the bandwidth of like the routers that their router are connected to otherwise limit the amount of bandwidth. If you exceed that bandwidth, you're going to see like packets not getting through. So you can sort of, it's a bit of a trade-off because obviously you're going to reduce the send rate, means you're not going to get as many updates through to the client, but at the same time you're aiming to like reduce latency and reduce the packet loss that the person would otherwise experience. So it's a bit of a trade-off there, and you probably need to kind of figure out what's appropriate. If you want to measure latency of the connection, basically you just track the time when you sent a packet, and then you track the time when it was acknowledged. You track the time when the packet comes in that acknowledges that, and you can just divide it by 2, and you can get the latency from the server to the client or the client to the server. So now that we've done this, now you have a protocol for real-time multiplayer. Should you actually use this, right? Well, no, because we didn't actually cover security at all. So nothing that I've kind of written here or explained here covers anything like preventing DDoS amplification, which if you're writing a raw UDP protocol and running it over the internet, you need to consider, because you can just totally spoof the source IP of a UDP packet. And so you can imagine a scenario where, say, your game servers reply with a larger message than the request. Somebody can just come along, create a packet with the source IP of the person they want to target, send it to your game server, and then your game server sends out massive like messages back. Excuse me. Sends out messages back to like the target that the attacker wants to hit, and then you're paying the bandwidth bill for that. So we didn't talk anything about packet replay attacks or encryption that's required on consoles. So for the underlying protocol, I recommend that you at least implement it once so you understand like how it works on a fundamental level and what decisions and trade-offs it's making. But then for your actual like production game, use something that's really well tested and has been used in AAA games like Netcode.io and Reliable.io. All right. I'm a little bit ahead of time, so before I move on to multiplayer architecture, did we have any questions first?
Just one question.
Yep.
When with 16-bit packet numbers,
Yes.
and 32-bit basically history flags,
Mm-hmm.
is there any reason to go particular values? Like, is there a reason we couldn't crunch the packet number down to like an 8-bit and have roll?
I mean, you really don't want to use kind of 8-bit because it's just not like a long enough history, I think. Even 16-bit is kind of not long enough history if you think about like a really long, like, hour-long game. So what you need to do is you actually need to detect when the sequence number rolls over, so that when, say, for example, if you start getting packet number 0, for example, coming through as the acknowledgement, then you know that the bit field is actually for 16 or whatever the max 16-bit integer is, so on backwards. So you actually do need to calculate that for when the sequence number rolls over. The reason we don't use something larger like a 32-bit number is we just want to save space, right? Every byte and every bit that we can save on like the headers that we're sending on every packet is more data we can send about the game. Yeah. Any other questions? Yes.
How many bytes is acceptable before it's considered a large packet?
Basically, if it's kind of going to go above the MTU, which is about 1500, so that's the maximum size you can reasonably fit in a UDP packet today on the internet, that number is that number's changed over time. It's I don't think there's a hard and fast rule. It really depends on like what routers happen to sit between like the player and like the game server along the the ISP, the transit providers, that sort of thing. But roughly speaking, 1500 is a pretty good number. And then once it's larger than that, you start using like large messages and splitting it up, because otherwise the routers will just drop the packets, right? Because UDP is unreliable. There's no obligation for a router to forward on a UDP packet. They'll just drop it if it's too big. Any other questions on network protocol? All right, cool. All right, let's get into multiplayer architecture. So what I'm going to run, oh, yes?
I have a question. Are there any internet standards on these kinds of protocols?
On these kind of protocols, not that I'm aware of. Like, different games are going to implement different things based on what they need. That's kind of why I recommend kind of looking at like netcode.io, because if you're an indie game, you probably don't really want to like devise your own protocol and have to deal with all of like the security aspects and stuff like that. But I'm sure AAA studios have their own requirements and will use other things. Yeah. Yes.
With regards to potentially out of order packets,
Mm-hmm.
do you just drop anything that isn't the reason?
So the question was, with regard to out of order packets, do you do anything with regard to the resend? In my case, in like what I've implemented, I just treat out of order packets as if they didn't arrive at all, and then if they were important, I'll resend them. The reason for that is kind of like if they're just like a player position, you don't really care about like something that's in the past, because you've already got newer information already anyway. So yeah, there's not really any reason. I guess you could probably like, the thing is you don't know if the sender really cares about getting it to the destination and what we've kind of devised here. But like, say for example, say you knew it was like a login response packet or something like that, and it came out of order, you could in theory accept it. I guess the question is actually really going to be like whether or not you already told the sender, if you're sending packets back to them, whether you already told them that you didn't get it, because that bit field is going to be set to 0. So that's something to think about. Yeah. All right. So what I'm going to run through in multiplayer architecture is interpolation with input prediction, deterministic lockstep, a little bit of deterministic lockstep. I'm going to kind of provide you with kind of like how do you determine what architecture is suitable for your game, the trade-offs that each make. There's going to be a little bit on implementing interpolation, and then a short explainer on deterministic lockstep. I haven't done it myself, so the deterministic lockstep part of this presentation is very much going to be based on research. And then a few other tips and tricks. So interpolation with input prediction, what is it? So it's server authoritative. The server sends state update changes down to clients only for things that have actually changed. Clients interpolate the received values, so you can imagine that you're rendering a game at 60 frames a second. You're not sending packets necessarily at 60 times a second, because it's going to use a lot of bandwidth. You want to kind of send them at a slower rate. And that means that the clients have to interpolate between those updates, because they're not necessarily going to get... It's not necessarily going to look smooth, right? If you don't interpolate it, it's going to kind of jump. The entity's going to jump all over the place. And then clients also perform input prediction to make the game feel responsive to the local player. You can imagine what it would kind of feel like if you are using WASD in a first-person shooter, and you have to wait for the server to acknowledge like your forward movement before you see anything, right? It would feel terrible. With the downsides to this, of course, are that with input prediction and interpolation, you kind of get paradoxes, because you can imagine a scenario where because you're predicting ahead of what the server's acknowledged and you're viewing all the other players in the past, there's a difference between what you see, where you see yourself as like ahead, and what another player sees where you're behind. And so you can get get paradoxes where players don't see the same scenario. A really common example of this is kind of like the Counter-Strike, where you get shot around a corner, right? Because, you know, one player sees you as being in the past where you're not behind that corner and they have a clear line of sight, while you're already around the corner and you're like, hey, that's not possible. So that's the kind of downside. You need to think about how that impacts your game design. Deterministic lockstep, what is it? Just as a comparison. So if you imagine your whole game simulation, and you say that state n, for example, then given only the player inputs, you can compute n+1 on the client without the server having to send information about all the changes to all of the entities that might be like typically server controlled. And that's really good if you have like a very large, constantly changing game state, like an RTS or a simulation where you might have thousands and thousands of entities, and there's no way you can possibly fit all of that data in messages going from the server to the client, just because there's too much to send. The downside, though, is you have to make things deterministic, and this can be very difficult. You can't well, when I say you can't simulate until you have inputs from every player, I'll kind of... Let's just ignore that line for a second, okay? And let's just ignore both of those bottom lines. They shouldn't be there. Okay, so how do you choose what you need? Every game is different. You need to think about, you know, how much game state do you need to synchronize between the client and the server? If it's a lot of state, then you probably need to think about like deterministic lockstep, because if you're limited by bandwidth, then you simply can't send everything. If you're extremely latency sensitive, then you need to think about input prediction and how you can use that. That's particularly important for like first-person shooters. And then, you know, you also need to think about like if you're using interpolation and input prediction, like how are you going to deal with the paradoxes that are introduced in that? And do those paradoxes turn up in a way that your players are going to notice and be like, that was unfair, or, you know, sort of thing. So how do we implement interpolation with input prediction? So as I kind of mentioned before, we're not sending updates for every other player's position down to a client at 60 times a second. That would just be kind of too much data. So we want to send those updates at, say, a regular interval, say every, I don't know, at 20 hertz, for example. And so what we need to do is we need to make that look smooth on the client. And so what you can do is you're receiving these updates for not just other players, but all sorts of entities. And you are storing this in a buffer for each entity. And then you're actually rendering all those network entities at some fixed point in the past, whether it's like 100 milliseconds, 200 milliseconds, whatever you feel is appropriate for your game. The less you render in the past, the more sensitive your game is going to be to packet loss. Because if you lose one of these, can I actually get a mouse on here? Oh, I can get a mouse on here. Great. So you can imagine that if you lose like all these state updates here, and we're saying that time is progressing to the right, so all of this red line here, which is what you're rendering, is going to be kind of moving here. If you don't have any state updates ahead of where you are now, then you don't really have anything to interpolate between, right? And so it's going to look like, excuse me, it's going to look like those network entities just like stop moving. And then of course the longer you put it in the past, the more subject you are to like paradoxes and things just feeling like they're really out of date. So it really depends on like what your game design is and what's appropriate for you. With input prediction, so now we can render like other players smoothly, but we also need to deal with the local player who wants to basically feel like that their actions are immediate. So what we can do here is we can track the latest update of the local player that we've gotten from the server, right? Because the server's basically taking your inputs, acknowledging them, and then sending down your latest position. So we can say, well, the server's last update for your position is at like tick 150, right? and then we can create a buffer of inputs, right, ahead of what we've sent to the server. And so we know, okay, well, we're at tick 170. We create a buffer of those inputs. And then every time we get an update from the server, we basically take out the inputs that were acknowledged by the server and then just replay the ones that the server hasn't yet acknowledged. And that allows us to basically make the game feel really responsive while also just like, it makes the game feel responsive while also dealing with like the fact that we have to reconcile what the server is telling us, which is that we might be behind where we are and still keep the game feeling responsive. Deterministic lockstep, again. So some considerations for deterministic lockstep if you were to implement this, and again, as I mentioned before, I haven't personally implemented this. Floating point determinism is really hard. It depends on your compiler, it depends on architectures. Yeah, it can be very, very challenging to get your compiler to produce deterministic results. Because you need to make sure that every client in the game is able to take the inputs and compute the next state and get like exactly the same thing that every other client will see, right? And if they don't produce, if it's not deterministic, then what will happen is your players will desync, and then you'll have to resynchronize everything, which, because the game state's so huge, means basically stopping the game, resending all the information down from the server to resynchronize the state, and then continuing the game from where it left off. So to kind of minimize like how much work is involved here, and I want to stress it's still quite a lot of work. You probably want to keep your like deterministic simulation separate from like the game engine you're using, and that will allow you to control like all the points that you need to actually make deterministic. Other various tips and tricks to think about when you're implementing multiplayer is like, can you hide latency with animations? Yeah, you can. Again, think about your game design and how you want the player to perceive things. Instead of interpolating the past, you can extrapolate the future position of players. The downside of this is it's often unreliable above a certain threshold, right? If you're trying to extrapolate a player's position 200 milliseconds into the future, there's a pretty good chance it's probably going to be wrong. It also probably doesn't work if your players have highly erratic movement or behavior. So again, think about like how your players moving around your map, and like, is that a strategy that can work for you? If you've got lots of physics objects, think about whether or not they really impact gameplay. Like, can you get away with like simply just not synchronizing something over the network? If it doesn't impact gameplay, yeah, you can probably get away without networking them. Can you combine architectures? Yeah, Factorio does this. Basically, there's a great blog post there, but they have a deterministic game state, and then they use input prediction on top of that. It's, again, it's very complicated. You still have to solve determinism, but it can allow you to make the game feel really responsive and be able to have an extremely complex game state that you would otherwise not be able to send over the network. Predictive deterministic lockstep, this is kind of a little bit different to that, whereas what Factorio does is deterministic lockstep with like input prediction on top. If you're doing sort of like predictive deterministic lockstep, you're actually rewinding the whole simulation and replaying the whole simulation again. With the pending inputs, obviously depending on the size of like the simulation you're running, that might not be practical, because if it takes a certain number of milliseconds to run one step of the simulation, you can't exactly rewind it and then replay it 20 times. But I've heard this being used for like fighting games, where you need that kind of determinism and very fast. Excuse me. I forgot where I was. Fighting games, yeah, where you kind of need that deterministic aspect, and you also need like the very like immediate response to player input. So paradoxes in the player view, if you're using input prediction and interpolation, As I mentioned before, this is kind of like the player being shot from around the corner. The more restricted a view a player has of their surroundings, the less likely they are to notice paradoxes. Excuse me. So for example, in like a first-person shooter, like you've only got like that 90 degrees field of view, it's much harder to see if someone's like shot you from behind and or doesn't have a clear line of sight. But if you were doing like a top-down game, then this can be very obvious, right? It's like, well, clearly you just shot through a wall. That doesn't make sense. Solutions for dealing with this are like incredibly game specific because it's going to totally depend on your game design. Before I go on to where to run servers, any questions about multiplayer architecture? Yes?
Is there any mileage in the pursuit of avoiding having to do a deterministic lockstep? Is there any mileage in having a server track what a client can see and only updating those entities? Something anyone does?
So the question was, is there any benefit for the server tracking, like in deterministic lockstep, the server tracking what the client can see and only sending information for those entities instead? Short answer is I don't know. I haven't particularly done deterministic lockstep.
To avoid having to do deterministic.
Oh, to avoid. Sorry. Is the question? Can you do that to avoid deterministic lockstep? I guess in what I would say is considered like the worst case, right? Because if the worst case is like the player is seeing 90% of the map and you really need deterministic lockstep at that point, then there's probably not a lot of benefit. Like once you're over that line of like you have to do deterministic lockstep, then you might as well just go and do the hard work to do it. Yeah. Any other questions? Yes?
This is kind of like almost a historical question, but the old GCAP games used to use some sort of near determinism because they could record demos which were mostly just player input, and they were able to sort of share the load between their multiplayer code and then their testing code for replay. Like they could run replay.
Oh, I see.
Is that still a valid wisdom, or have we sort of collectively moved on and said that that was too much work and it's not worth it for the benefits we get?
I'm not sure. Personally, I would say like deterministic lockstep or determinism is really hard. So I wouldn't really go down the determinism route unless you really need it. That would just kind of be my advice. I can't really speak to that specific scenario of using those using that data for replays, but I would say that probably realistically you could. Yeah, I really don't know. Sorry. Any other questions before I go on? No? All right. So where to run servers? So just really quickly, dedicated servers is basically you as the game developer, you're hosting the game servers and players connect to them. Peer-to-peer or player hosted is like, you know, the game picks a random player in the match and that player hosts and all the other players connect to them. As an independent developer, it can be really tempting to pick the second one because, hey, I don't have to run dedicated servers and that'll be really cheap, right? But it's not really a great experience necessarily. You can imagine that, say, the game picks a random person to host and that person is playing on like a 5-year-old laptop over Wi-Fi on like an ADSL copper connection, right? Like it's not going to be a great experience for the other players in the match who might have like fiber and they're just like, why is this game suck, right? So you should really plan to use dedicated servers at launch. I would recommend you start there unless you've got a really good reason not to, because people who have like a poor experience in the game are not gonna stick around. They've got other games they could be playing, and you want to maximize your retention of players. And yeah, all right. So this is the like obligatory sales pitch part of the talk. Just fair warning. So you've implemented the protocol correctly, and you've chosen the right architecture. You've considered the game design impacts, and you're running dedicated servers. And some players still have a bad experience. And why is that? Well, you're not in control of the network, right? The public internet can do whatever it wants. And you can't really control that. But what if you could, right? What if you could tell the network what you want, and what you're willing to pay, 10 minutes, okay, and it would just go do that, right? If you could just say, well, I need 80 milliseconds or less for latency for my game, and then it would try and optimize and find the best route that meets that requirement. So Network Next is a marketplace for premium network transit, and like I just mentioned, so suppliers basically sell network transit that they have available that would not typically be used for the public internet. And then game developers specify what you want from the network. So I want 20 milliseconds latency reduction or greater, and the price that you're willing to pay. And then every 10 seconds for every player, we run a bid to find the best route that meets your requirements over, in aggregate, all of those suppliers. This is a worldwide map. This is probably a little bit old now, but this is a worldwide map of every player who received 20 milliseconds latency reduction or greater through Network Next. And when I say 20 milliseconds latency or greater, I really do mean or greater. There are some pretty poor connections out there that are not necessarily bad connections at the edge. They're poor ISP routing internally, or network transit providers that just don't peer well with one another. Or they're just ISP misconfigurations that last for a couple of days and then go away. And because, as I mentioned, we dynamically route around these issues, or we dynamically route traffic every 10 seconds, we can respond to these kind of situations very quickly and reduce latency for players who would otherwise probably get a bad experience and quit. So, take-home messages, network protocol, implement it so you understand the concepts, and then use something well-tested for your actual title. Multiplayer architecture, understand your game, understand what trade-offs you want to make and what design impacts that's going to have. Every game is different. There's no generic solution that's going to work for everyone. Use dedicated servers at launch, unless you've got a really good reason. And if you're interested in lower latency of your players, come speak to me after talk about Network Next. Thank you very much for listening to me talk. A few other things, Network Next is hiring, so if you're interested in multiplayer stuff, also come see me. This presentation is at that link, and all of the demos that I've put up today are on GitHub. There's also the link, and there's also a ton of links on that GitHub as well to like blog posts and other resources that are great to look at if you're going down the route of implementing multiplayer. And thank you very much. We've got about 7 minutes for Q&A, so if you have any questions that have not already been answered, there is a microphone up the front. Oh. Microphone. Yeah.
Hi.
Yep.
Just curious about how you think 5G is going to, and local compute or edge compute is going to change some of your assumptions.
Edge compute is actually quite good for us because it means that we're able to basically have more places where we can route traffic through more or steer traffic earlier to a better route. The closer that we can get compute to the edge actually enables us to route better over Network Next. Yeah.
Do your clients tend to have like specific centralized servers hosted somewhere, or do they tend to still use Azure, AWS, etc.?
It depends on the client. At the moment, Network Next is very focused on like games with dedicated servers. We don't do like player-hosted servers, for example. But yeah, it varies. Yeah, sure.
Hello. You mentioned that if users have a peer-to-peer connection, that it will be a worse experience if the host is a has a really bad connection. Is there sort of like a method available or something that's been done before where it determines the best host to make sure that it's the best experience for everybody?
I mean, you probably could do something like that, but again, you're still relying on someone's home internet to basically run the game, and that is going to impact everyone else's experience. So I would still recommend planning to use dedicated servers from the start. Yeah.
Cool. Thank you.
Thanks. Yes, at the front.
Any thoughts about matchmaking and like maybe when the game is starting, trying to associate players in similar geographic regions, or do you have an idea what's best practice there?
Not really. That varies per game. Yeah, that's kind of outside the realm of like the network protocol and multiplayer architecture stuff. Yeah. Sorry. Yep.
Great talk. Regarding MTUs being 1,500 bytes, if you're consistently sending, like how bad is the experience for players if you're consistently sending packets which are being segregated across multiple packets, like sending messages segregated across multiple packets? Like if you're sending, like there are some certain games, there's a YouTube channel where this guy goes through and goes, this game is having, sending at the very start, for the first 10 minutes of the game, is sending player positions across multiple packets or inputs and stuff. Is that massively bad? Do we care that much at this point?
You mean what happens if you send packets that are larger than 1,500?
Consistently for like player positions, inputs, movement, shooting. Like, do players notice that much? It's sort of
well, if you send above if you send above the maximum MTU and the packet's going to drop, then yeah, because you might not get any information through at all. For things like player positions and information like that, you really want to keep it under 1,500 based on your tick rate. So if you're sending 20 times a second, you want every one of those packets to be under 1,500. So you want to optimize both your usage, like what I was saying before about think about, do you really need to network something? Do you need to send the information? And you really want to optimize the serialization, how you actually send messages, which is something I didn't talk about at all here. But you really want to make sure that you're not sending or wasting those bytes, basically. Yeah. Anyone else?
So once your game state has gotten to that 1,500 byte limit, and you don't want to divide your game state up into multiple packets because then you add extra latency onto your transmission. I guess the next step everyone goes to is, as you just mentioned, improving serialization and compression. And there's a few different avenues people normally go down. One, which I think has been kind of touched on, is selective sending of data. So everything outside your field of view, maybe don't send that in this packet. But the other kind of two big ones that I often hear a lot is delta compression. So taking what we've got previously and using that to compress data for the next one. And then arithmetic compression, or basically zipping all your data. Yeah. And I'm wondering, is there any process for combining the two, like using arithmetic compression with delta compression, so you're compressing against past states using more advanced compression methods?
Yeah, I'm not sure. Sorry. Yeah.
Concerning your network next technology, what is the performance cost to sort of negotiate and trade on the network live while you're playing your game? So every 10 seconds you say...
Oh, you mean well, all of the bidding happens on our back end. So basically...
Yeah, but isn't there some delay? So let's say nothing meets my price and then I'm stuck with a packet that hasn't been sent.
Oh, no. So basically what we do is we're always sending the traffic out straight away, and then we'll look at the past 10 seconds experience to determine the RTT and jitter and packet loss, and then we'll say, well, the public internet experience that you got for the last 10 seconds is worse than the route that we can give you at the price you want. And then we'll be like, okay, start routing over network next instead. But that's all seamless from the sending packet perspective. Yeah. Does that answer the question? Yep. Yes.
Kind of on with the last question. Does that mean you're using Is it like a plug-in type thing that you
Yes,
use
yes.
to-
So
okay.
it's an SDK that you put in your game, and basically it replaces like the UDP send and receive, and then just you specify in the portal like what you want from the network, and then the SDK makes it happen basically in combination with our backend. Yes, down back there. I think that's
Last question.
the last question. Yes.
How well does Network Next work with middlewares like, say, Photon?
Well, Photon is basically like player hosted or peer-to-peer. They basically pick like a host at the start of the game. So as I mentioned before, we don't support kind of player hosted scenarios. We're basically concentrating on dedicated servers at the moment. So yeah, it doesn't work for something like that. Yeah. All right. Thank you very much, everyone.